Right, so for the last part of the moment series, it's going to be looking at tilting. So what tilting is when a rigid plank is on the point of tilting or rotating about one pivot, the reaction or the tension in the other pivot is equal to 0. So what we mean by that is if I was to show you an example, so if I have a rigid plank and I've got two pivots, okay, and I put a mass here, let's say a mass of W or weight of W, what this is going to do is create a clockwise moment, right? And therefore it's going to push downwards, right, in a clockwise direction. Now, if the question says it's about on the point of tilting about B, what this means is that the reaction force at A, because we know we have reaction forces here, right, RA and RB, is actually going to be equal to 0, okay? You can imagine that, like, if I was to push down on W, this plank will slightly lift up, right? Like in this kind of, this is a bit eccentric, but it's going to lift up, right? Which means reaction forces only occur when there's a contact between two things. And if it lifts up, then it's lifting up off the A pivot, and therefore there's going to be no reaction force at A. So the way I've drawn it is a bit, I've exaggerated a lot, but you just have to imagine that, oh, it's going to slightly, it's about to lift up, therefore the reaction force at A is going to be 0. Same thing with like the tension, right? So there'll be like, if I have two strings like this, like here, let's call this TA, TB, and I put another mass here or weight here, and they'll say it's on the point of rotating this time, rotating about B again, which means that this is now going to push it down and lift up a bit, and therefore there's going to be no tension, or the tension in A is going to be equal to 0. So if it's rotating or tilting about a certain pivot, the other pivot's reaction or tension forces is equal to 0. That's what you have to just imagine or remember for this kind of situation. Right, so we have a plank AB of mass 12 kilograms and length 3 meters. It's in equilibrium in a horizontal position resting on supports C and D. So let's go back drawing first. So we have a plank, we have AB, okay, and it's on two supports C and D, so C and D, where AC is 0.7 meters, this is 0.7 meters, and DB is 1.1 meters, so this is 1.1 meter. The whole plank itself was 3 meters, right? Okay, so a boy of mass 32 kilograms stands on the plank at point E. The plank is about to tilt about D, okay? So we have the reaction forces RC and RD. So if it's on the point of tilting about D, we know the other pivot's reaction force, in this case C, is equal to 0. So that's a condition that we have to be aware of, RC equals to 0. By modeling the plank as a uniform rod and the boy as a particle, calculate the distance AE. So it's a uniform rod, meaning that the weight, which is 12G, is in the middle. Now, we just have to identify where the buoy is going to be, because like you see here, the buoy is 32 kilograms and he stands on the plank at a point E, which we don't know. So in this case, as we said, we have to identify where this position is going to be. Well, the way we do that is, if RC is to be equal to 0, i.e. is by the point of tilting about D, the buoy has to be somewhere to the right of D, right? That way it will lift up or press down on the right of D and lift up off C, okay? So that's how we know where the buoy is going to be. So it's going to be 32G. And they want the distance from A, so let's call this distance to it as X, like this. So now we've done the drawing, let's do moments. So we're going to do moments about D, going clockwise as positive. As you can see, with the 32G of the buoy times the distance. Right, so this is the distance to the pivot D, right? So as you can see, X is the distance from A to the buoy, A to E. So from A to D, that's the distance of 1.9 meters, right? So to get A to E, it's going to be X minus 1.9. Right, we also have this 12G, so 12G is going to act anti-clockwise, it's going to be negative 12G times. The distance is 1.5, so 0.4. And we don't have to include this RC value, remember, because if RC is going to be equal to 0, so therefore we don't need to include the RC in our calculation. And now we just have to equate this equal to 0 like this. Yeah, we just have to work out this calculation now, and you should get that the X is going to be equal to 2.05. Let's try another question. So the plank AB has length 4 meters. It lies on a horizontal platform with the end A lying on the platform and B up over the edge. The edge of the platform is at the point C. Jack and Gio are experimenting with the plank. Jack has mass 48 kilograms and Gio has mass 36 kilograms. And they discover that if Jack stands at B and Gio stands at A and BC is 1.8, the plank is in equilibrium and on the point of tilting about C. So let's go back drawing it like this. As you can see, we need to identify some pivots. So the pivots in this situation are going to be at A and C, like here. So A and C. Right, so what do we know? So if Jack, they say that if Jack stands at B, so B is at the edge of the platform, so Jack's going to stand here. And Jack has a mass of 48 kilograms, 48G as the weight. and geo stands at A, so A is going to be here at the pivot. G weighs 36 G here, like this. And BC, this distance is 1.1 meter. The whole plank itself is 4 meters, right? So this distance here is going to be 2.9 meters. And therefore they say it's on the point of tilting about C, meaning that we have reaction forces RA and RC, right? If on the point of tilting about C, we know that RA is going to be equal to 0. Right, by modeling the plank as a uniform rod, so it's a uniform rod, and Jack and Jill as particles find the mass of the plank. So uniform means that it's in the middle, and it's going to be mg, like so. Right, same thing, we're just doing moments now. So we're going to do moments about C, because that's where it's tilting about. So we're going to do 48g times the distance to C 1.1 minus, now you can see here we have two forces RA and 46g, okay? We don't have to include the RA because that's equal to 0, but we do have to include Jill's weight, so it's going to be 36g times the distance, which is 2.9, and it's going to be negative. And we also have this mass of the platform, so mg times the distance here, well the distance was 2.9, but it's in the middle, so it's going to be 0.9 like this, and that's equal to 0, which I can work out and get that m is going to be equal to 36 kilograms, like so. Right, they now alter the position of the plank in relation to the platform so that when Jill stands at B and Jack stands at A, the plank is again in equilibrium and on the point of tilting about C. Find the distance BC in this position. Okay, so it's the same situation, but now it's on the point of tilting about C, which means that RA is still going to be equal to 0. And the mass of the plank is now 36. Let's do another drawing like this. So if A here, we have C here, the mass is still, or the plank is 36g now. Jack still stands at A, or sorry, Jack stands at A now, right? So Jack's weight is going to be 48g here, like so. And then Jill stands at B, so B is going to be here, so she weighs 36g like this. And we have this RA and RC like this, and RA is still going to be equal to 0 because it's on the point of tilting about C. Let's say find the distance BC. So now this is B here, we're trying to find this distance X like here. But same situation, we just have to do moments again. So we're doing moments about C, going clockwise. So we have this 36g, the mass of Jill, times the distance X, which we don't know. We also have the mass of, or the weight of Jack, so it's 48g, times the distance. Now we don't know this distance because we don't know X, but this one we can call 4 minus X because the whole distance is 4 meters, right? So it's going to be 4 minus X like so. We also include the weight of the plank, so it's minus 36g times the distance once again. Well, it's still a uniform rod, right? So which means that it's still in the middle. So this distance here is going to be 2 meters still, meaning that this distance is also 2 meters. If C to B is X, then this distance C to the mass will be therefore 2 minus X like this. And that's all going to be still equal to 0 because it's still in equilibrium. If I were to work it out, then X will give you 2.2 meters like so. So the calculation itself is not too difficult, it's just making sure you know the positioning of each individual particle and the mass and whether or not it's a uniform or non-uniform, and also the fact that it might be tilting about a certain pivot.